SwayamPrabha. Digital India. Educated India.
In this lecture, let us continue our discussion on hypersonic flight trajectories, after which we will talk about basics of wave rider design, and we will do a recapitulation of the boundary layer equations before we move on to reference temperature method, which is a very interesting engineering significant method. In the previous lecture, we had discussed about these equations, where we said that for most of the entry conditions back into the Earth's atmosphere or any planetary atmosphere, we talk about shallow values or small values of the angle theta, and therefore, we have these simplifications that sin theta can be approximated to 0, cos theta to 1, and of course, the mass of the vehicle is its weight by the acceleration due to gravity, from which, based on the equations that we wrote along the flight path and normal to the direction of the flight path, when we impose these simplifications, the equations would reduce to these forms. And then if you look at the equation where drag is figuring, you can convert the drag into its coefficient. So, the drag coefficient figures here along with the rho v square s term, and then you are able to gather a few terms together to form an expression which is significant. The W by C d s is an important expression which we call as the ballistic parameter, and it definitely influences the flight path of the entry vehicle. It is the equation that defines its movement along the flight path, the balance of forces. And if you have a purely ballistic re-entry, that means a case where there is no lift, you may imagine that capsule like surfaces would have that kind of a behavior, where because of the symmetry of the body along the flight path direction, you would end up having only drag acting on this body. It is a non-lifting body until and unless you pitch the body to a certain orientation where it becomes a lifting body. So, W by C d s is the only parameter which will govern the flight path for a given entry angle, the entry angle being the angle theta here. Expressing the lift in terms of the lift coefficient, similarly from the second equation, which governs the balance of forces in the direction normal to the flight path, we find that the W by C L s is a important term here, which we call as the lift parameter. It definitely influences the flight path of a lifting entry vehicle, where C L is not equal to 0. We drew a schematic diagram of a vehicle which looked more like this, if you recall, where we talked about scramjet engine powering the vehicle if it is a kind of a cruising vehicle. If it is a gliding vehicle, then you are essentially talking about a zero thrust condition. And then in most of the vehicles in general, you might end up seeing that both of these would influence the flight path of the vehicle to a greater or lesser extent. And ultimately, the consequence is we end up defining flight paths on the velocity altitude map, where we essentially lay emphasis on the particular parameter which is more significant, either the ballistic parameter or the lift parameter. Any one of them would be significant for a particular vehicle, and we lay more importance to that based on the vehicle design. And of course, velocity altitude maps are convenient diagrams to illustrate various aerothermodynamic regimes of supersonic and hypersonic flight vehicles which are traveling within the atmosphere, or most importantly entering the atmosphere. So, we talk about aerothermodynamic environment because of the extremely high heating rates in a hypersonic entry condition. We had looked at this plot in the previous lecture too. We have put in more details into the plot now. The important ones are that you can see two dashed lines. One is blue colored, the other is red colored, and apart from that there are a few more markings that we have put. For the blue color, we have marked it is a typical trajectory of a ballistic entry from Earth orbit, and we have marked a typical trajectory of a ballistic entry from lunar mission. It could be mission from some other planet too, for example Mars. And then we have marked escape velocity for lunar entry. We have marked satellite velocity for the other trajectories, and you can see the other plots that we find over here. The curves are essentially catering to the typical trajectory of lifting entry from Earth orbit. So, there are a number of trajectories that we are talking about because we are talking about a velocity altitude map. Apart from the flight trajectory path or the profiles which they follow for the VH kind of regime that they pass through, the velocity versus altitude regimes that they pass through. Additionally, the important part beyond that is the chemically reacting mixture of air, mixture of gases which comprise the air. So, the air is no longer the normal oxygen, nitrogen in their molecular forms, but numerous species which exist under the extremely high heat transfer rates which are now existing around the vehicle, and thereby you end up seeing that at the higher end of the velocity ranges, when they are about to enter, they fall into different regimes. For example, if you talk about a typical trajectory of ballistic entry from a lunar mission, you can clearly see that it passes through a velocity range over a fairly wide range of heights, where ionization is a predominant phenomena, and then as it gradually slows down, the ionization may gradually go away to the dissociation of the gases. So, nitrogen dissociation, oxygen dissociations which are occurring at the lower velocities. So, if you think the other way, as you are speeding up, then you look at vibrational excitation which begins at about 2 to 3 kilometers per second range over a fairly wide range of heights reaching up to about 100 kilometers. There is not much variation in that corridor where you see these dashed region indicating the vibration excitation, and then if you speed up further, you are talking about oxygen dissociation which spans through about 3 to 6 kilometers per second at sea level, and the region sways towards the left slightly, which means it initiates at lower velocities at higher altitudes. And then there comes a region of nitrogen dissociation starting from 6 to about 10 kilometers per second. Again, that region sways towards the left at higher altitudes, and the regions are marked with initial and final bands where 10% completion and 90% completion of the respective phenomena is indicated, which means that a gradually speeding vehicle, if it follows this kind of a path, would increasingly see the presence of oxygen dissociation after the vibrational excitation. Beyond that, if it speeds up further, oxygen has already dissociated completely. Beyond that, you will see nitrogen dissociation setting in and a lot more species forming within the mixture. And then finally, if it speeds up to a level like this, then you would also start seeing ionization in the medium, which means that whether you speed up or you slow down through those velocities at those altitudes, you are going to see these chemically reacting effects in the medium, which is a very, very important fact to remember. And therefore, velocity altitude maps have a lot of significances associated with them, where you are populating the graph with so much information. Let us try to look at some more points in the form of observations that we just saw in the map. The above two equations that we see over here illustrate the importance of the terms in determining the flight path through the atmosphere of a vehicle returning from space, as shown in the velocity altitude map. We have appreciated this already. The figure shows two classes of flight paths. One is ballistic entry, governed by the parameter W by CDS, and the lifting entry governed by the parameter W by CLS. The vehicle enters the atmosphere at either satellite velocity from Earth orbit or at escape velocity, example return from a lunar mission or some other planetary mission. As it flies deeper into the atmosphere, it slows as a result of aerodynamic drag. An interesting point is that vehicles with larger values of any one of these parameters penetrate deeper into the atmosphere before slowing. Therefore, if you are talking about a lifting entry, then larger value of W by CLS will push the trajectory deeper into the atmosphere before it slows down, which means it loses altitude without losing much velocity, thereby dipping to a deeper trajectory. The same happens for a ballistic entry 2. If it has a higher value of W by CDS, what would happen is that it would move down further before it starts slowing down. So, that is the point we are trying to make. The W by CDS curves in general lie below the W by CLS curves, which is already observed from this diagram. So, we once again looked at velocity altitude maps and tried to recapitulate the significances and add on to the information to some extent. We recall that for efficient cruise at hypersonic velocities through the atmosphere, we need to have a fairly good aerodynamic performance in the form of a reasonably high L by D ratio. This is something that we had discussed in our previous two lectures. And as a consequence of that concern, we take up a particular design, wave rider design, and try to understand that what design feature enables it to achieve superior aerodynamic performance at hypersonic velocities. That means, irrespective of the very large wave drag, these kind of designs are able to achieve better values of L by D than generally achieved by generic designs. And therefore, it is interesting to see the design feature which makes it quite special. We start with a simple sketch here to try to explain that what might happen if you expose a sharp wedge to a supersonic or hypersonic flow coming and impinging on the body. So, if it is a case of zero angle of attack, then we know that two oblique shock waves would form symmetrically on the upper and lower sides of the body, and therefore, the pressure distribution would be behaving symmetrically on the upper and lower surfaces, it is essentially also a non-lifting body in such a case. And here of course, we consider the flow to act like an inviscid one, and then we raise the question that can we make one of these waves to graze the surface or practically vanish. In that case, we actually orient the flow in such a manner that that same u infinity is now going to come in with some alpha. So, there will be a certain alpha at which it starts grazing the surface. So, it is basically theta by 2. If you incline the incoming flow direction at an angle of theta by 2, then an inviscid flow that comes in that manner would exactly graze the surface, and therefore, there is no possibility of a shock forming there. Remember that if you consider boundary layer forming on that, that means you start considering a viscous flow, then nevertheless there will be a leading edge shock formed even if the flow orients itself with the body surface. But here, because we are talking about an inviscid flow, in this condition where the angle of attack is exactly theta by 2, we are likely to see a grazing of the flow over the surface. And then what happens is that there is only one shock which is formed on the lower surface. So, this is the lower shock, and then the deflection also appears to be larger to the flow. It is the entire wedge angle which will be acting as a deflection angle instead of the theta by 2 deflection angle which the flow saw in the previous instance. Therefore, in a two dimensional sense, we can understand that there could be a situation where the body can actually kind of ride the wave, in the sense that the upper wave is no longer surrounding the body, but it is exactly incident on the body surface. We try to look at it that way. So, if we imagine that concept coming in over here, then this is the wedge that we are talking about, and then this is the shock that we can see at the bottom. And can we imagine a body which is occupying this volume that we are talking about, which is currently occupied by the wedge and the lower shock, and then we imagine that the body comes in and the wedge goes away, and the body is shaped in such a manner that the leading edge of the body exactly rides on the wave. So, this is one portion of the leading edge of the body which has a sharp tip moving right from the leading edge till the trailing edge. The same thing happens on the other side, most of which is not visible, and then apparently this body shape is kind of riding the wave. Again, we are talking about an inviscid free stream flow grazing past the upper surface of the wedge as well as the upper rib of the body. So, we have a kind of a carrot shaped lifting surface. The upper rib of the wave rider is kind of aligned with the flow direction. So, this concept helps us understand how vehicle shapes can be designed in a manner that they ride a shock wave, and then you can have a curved shock wrapping around a curved wave rider body. So, this is a curved wave rider. Let us imagine that it has been shaped in such a manner that it is more optimized in terms of lift and drag, or lift to drag ratio, or absolute values of lift that it can generate is better than the carrot shaped body. But the main idea is that the upper surface of the body is perfectly wetted by the flow, and the curved shock exactly wraps around, so that it kind of is coincident with the leading edge of the body, and then you can see it moving down in the lower side alone. There is no upper portion of the shock because it is coincident with the body. The maximum lift to drag ratio for a flight vehicle is a measure of its aerodynamic efficiency. We are aware of this already, Unfortunately for supersonic and hypersonic flight vehicles, as the free stream Mach number increases, the L by D max decreases rather dramatically. This is because of the rapidly increasing shock wave strength. So, we are talking about a large rise in the wave drag and therefore, consequent poorer values of L by D max. Note that the variation of L by D with angle of attack for a hypersonic flat plate as calculated from the Newtonian theory, which you learnt in the earlier part of the course, it actually gives us the result that it varies as cot alpha. So, L by D theoretically approaches an infinity value as the angle of attack approaches 0, since the L by D ratio with the inviscid theory is given by cot alpha. In reality though, the viscous shear stress acting on the plate surface would cause the L by D to peak at a low value of angle of attack and to go to 0 as angle of attack approaches 0. So, these are some of the facts that we know from basics, and we are trying to plot one of those results here. We just talked about the flat plate behavior. Why we are talking about the flat plate behavior is that is the simplest geometry we can think about, from where we can extend the concept to a wave rider later, and the simplest geometry gives us the L by D ratio variation of cot alpha. So, the inviscid result says that as alpha tends to 0, the L by D exponentially rises towards infinity. However, the reality is that if you include the skin friction, then there will be a maximum L by D at a small angle of attack, and then it dips down to 0 as alpha tends to 0. So, this is the connection between the theory and the reality. Keeping all this in mind, we next move on to see typical lift and L by D variations for wave rider kind of geometries, and then you see that typically the lift variation for a wave rider geometry looks like this, while the L by D for the wave rider looks like this. Correspondingly, the lift variation for a generic vehicle, which is a non-wave rider design, has a shallower profile than that of the wave rider, and also correspondingly the L by D for the generic vehicle is also lying lower than that of the wave rider. So, there is a class of hypersonic vehicle shapes that generate higher L by D than other shapes. So, these are the wave riders, and in these vehicles the shock is attached all along the leading edge. Because of this, the vehicle appears to be riding on top of the shock wave, and therefore, it is called as a wave rider, because it is riding on top of the shock wave. That is the feeling. This is in contrast to more conventional hypersonic vehicles, where the shock wave is usually detached from the leading edge and other blunt regions of the body. So, this is basically the difference between the two cases. The advantage of a wave rider is that the high pressure behind the shock wave under the vehicles does not leak around the leading edge to the top surface, because you are kind of making it airtight. This feature ensures that the flow field over the bottom surface is kind of contained and the high pressure is preserved, and therefore, this is the mechanism by which it ends up producing higher lift than other vehicle designs. In other designs, if there is a communication between the flows over the bottom and the top, the pressure tends to leak, and therefore, the integrated pressure on the bottom surface reduces, and therefore, there is less lift. And therefore, due to this loss of lift, a non-wave rider design must fly at a larger angle of attack to produce the same lift as the wave rider due to the shallower lift curve. So, if you go back to this curve and you say that, well, I have a particular lift requirement, then you see that the alpha corresponding to the non-wave rider is definitely larger than the alpha corresponding to the wave rider. The other penalty that happens due to that is that the L by D ratio for the wave rider for that particular lift requirement will stand over here, while correspondingly for that alpha the L by D of the non wave rider will also be lesser than that of the wave rider. As is evident, the lift curve for the wave rider is considerably higher because of the pressure containment as compared to the generic vehicle design. Because the wave rider generates the same lift at a smaller angle of attack than does the generic vehicle, which must fly at a large angle of attack, the L by D for the wave rider is considerably higher than that of the generic shape. So, we already saw that on the plot. Therefore, for sustained hypersonic cruising flight in the atmosphere, the wave rider configuration has a definite advantage. So, this is the relevance of the topic that we are discussing, why we are interested in such efficient aerodynamic designs, so that hypersonic sustained cruise becomes a reality. With this, we move on to a brief recapitulation of some results of compressible laminar boundary layer over a flat plate. Before we discuss a very interesting concept, the reference temperature method. These are things we covered much earlier in the course. If you recall, in the 4th week in lectures 19 and 20, we talked about the self-similar solution of the compressible boundary layer equations on a flat plate. And remember that we were talking about laminar boundary layer in that case, and we talked about reduction of the partial differential equations to a pair of ODEs, and a numerical technique to solve it was a shooting technique. We had these two ODEs to be solved. The gas was considered to be calorically perfect. No chemical reactions were modeled. Dissociation, ionization effects in high temperature were not considered, and also vibrational and chemical non-equilibrium were not accounted. As you can understand that if you are to model all these things, then the ODE structure will probably fall apart, and you will have to account for all these effects in a more complete way. The full compressible Navier-Stokes equations were not solved in this case, where we were talking about solving the two ODEs. These equations were simplified to the boundary layer form, and again further simplified for the flat plate geometry. And then we came up with some interesting results like this, results for laminar boundary layer, the compressible boundary layer non-reacting flow solution for a flat plate, where we were talking about the variation of the CF root REX as a function of Mach number for both isothermal as well as adiabatic walls. And we also talked briefly about the incompressible flow result, where it fits in this perspective. We talked about the skin friction coefficient, how it comes out in the compressible case. This was the incompressible Blasius solution, and we said that the functional form for the skin friction coefficient for compressible case involves many other parameters, most importantly temperature ratio, Mach number, with E in the subscript representing the edge of the boundary layer. Additionally, we have Reynolds number, Prandtl number, and ratio of Cp and Cv, that is gamma. Similar trends were seen in the heat transfer coefficient by the Reynolds analogy, and then as we saw the incompressible result here, we further remarked that the compressible result will again show functional dependence on a number of parameters, just like the skin friction coefficient. And based on that, we come to the concept of reference temperature method, where we say in the beginning that it is an approximate engineering method for predicting skin friction and heat transfer for both laminar and turbulent hypersonic flow. So, this is a very handy tool, which without explicitly solving the ODEs which we were talking about, which give us the solution of the compressible boundary layer equations, we can still generate fairly good estimates of skin friction and heat transfer both in the laminar as well as turbulent boundary layer cases for hypersonic flow. Not only hypersonic, I should also mention that it extends to supersonic flow too. I mean, it starts from the supersonic regime for the compressible flow and rather extends to the hypersonic regime as long as we can operate within the simplifications that we already mentioned about. It is based on the simple idea of utilizing the formulas obtained from the incompressible flow theory, wherein the thermodynamic and transport properties in these formulas are evaluated at some reference temperature, and that is indicative of the temperature somewhere inside the boundary layer. So, we do not explicitly specify the location where we are talking about within the boundary layer, but we say it is somewhere. In this fashion, in some sense the classical incompressible formulas are corrected for compressibility effects, and therefore, we are essentially extending them to a compressible situation. These reference temperature or reference enthalpy methods have enjoyed frequent application in engineering oriented hypersonic analysis, and they were initially conceived by some of the scientists named here, Rubesin, Johnson and Eckert. So, we have more interesting things coming up in this context, but because of paucity of time we will move it to the next lecture. Let us conclude here by saying that in this lecture we completed the discussion on hypersonic flight trajectories. We then discussed about basics of wave rider design and the reason for its superior aerodynamic performance. We recapitulated the compressible boundary layer equations in the laminar form, and we started our discussion on reference temperature method. Thank you.